section.
We will start with intros about PMC, simulation tool categories, and Siemens PLM Technomatics plant simulation. Then we'll cover optimization, including how to find and break bottlenecks and optimize throughput, workers, and energy. Then we'll wrap things up with the newest major plant simulation features, and finally, we'll take your questions. Simulation tools fall into several categories. Since people can often be unaware of the differences among the tools or even the existence of any of them, we'll briefly explain the major categories. Kinematic tools like Siemens Technomatics RobCAD and Process Simulate Robotics lets you analyze the real-time motion of robotic work cells, optimize cycle times, optimize welding sequences, and increase process quality. Ergonomic tools like Jack and Process Simulate Human let you analyze human motion and optimize the ergonomics of human operation to enhance worker efficiency and minimize injuries. Note that the focus here is on the actual motions that a worker makes in order to complete a task. Computer-aided engineering tools like NXCAE let you analyze specialized items like thermal and flow analysis and finite element analysis early in the design process. This results in better performing products. Computer-aided manufacturing tools like NXCAM let you analyze specialized items like tool design, NC programming, feature-based machining, and collision detection. This automates the development of molds, dies, and fixtures for higher quality, lower cost, and faster turnaround for machining. Pedestrian flow tools like Pedestrian Dynamics and AnyLogic model the behavior of people moving on sidewalks, stairs, and escalators, etc., in stores, stadiums, airports, etc., both in normal and evacuation scenarios. The pedestrians are aware of others, alternative pathways, and obstacles around them. Like in the real world, their behavior is random, including walking at different speeds, going around obstacles in different ways, passing each other, etc. As opposed to the first categories above that focus on individual work cells, individual workers, or products, discrete event tools like Plant Simulation, Simulate, and AutoMod let you analyze the operation of an entire department or facility and optimize overall items like throughput, buffer or inventory sizes, scheduling, and workers. Discrete event simulations are also often referred to as throughput simulation. Although all these tools are really cool, the focus of today's webinar is on my favorite, discrete event simulation, and more specifically, how this type of tool allows you to optimize workstations, lines, and whole plants on up to an entire enterprise consisting of more than one facility. For those who may not know already, discrete event tools like plant simulation let you analyze the operation of an entire department or facility and optimize overall items like throughput, buffer or inventory sizes, workers, and scheduling. Plant simulation is overflowing with useful features, but I'd like to point out 3 of its unique key features. Object orientation provides intuitive use of powerful, built-in, and custom-made objects that let you build models quicker. Hierarchy lets you structure complex models in an intuitive manner. It also makes it easier for you to make changes without having to tediously rearrange things like other flat-structured products require. Inheritance lets you make changes in one place. All children are changed accordingly. This ensures quality and saves you a lot of time. PlantSim's analysis tools include a unique bottleneck analyzer that helps you to pinpoint bottlenecks, a real time saver. Sankey diagrams let you see the flow of material. The thicker the line, the greater the flow. This can help you verify that the model accurately represents your facility and can help you to pinpoint potential problem areas and balance out the flow. And Gantt charts display resource utilization over time. Visualization options include 2D. This option is quick in two ways: quick modeling time and quick simulation runtime. CAD integration lets you import a CAD file and use it to place modeling objects in exact location. Some people prefer this. Others prefer not having to place objects this way. The great thing is that PlantSim accommodates both types of users. A 3D view is optional, but it is very easy to auto-generate and enhance. The great thing is that both 2D and 3D views are available, so you can take advantage of each one's strengths without being limited to one or the other as in other products. The goal of most simulations is to increase throughput, often expressed as jobs per hour, jobs per day, etc. A two-step process is repeated until the desired goal is met. The first step is to locate the main bottleneck. The next step is to break the bottleneck with what-if experiments. So how do we find a bottleneck? You look at the simulation output statistics like percent working and percent block and look for clues. You could look at the detailed statistics reports of individual stations as shown here. Better yet, you can use other PlantSim tools that help you pinpoint bottlenecks faster. One clue of a bottleneck is a station with the lowest block time. Another is lowest waiting time, also called starve time. Highest working time. Upstream buffers mostly full. Downstream buffers mostly empty. Upstream workstations blocked. And downstream workstations waiting or starved. There are several ways to break bottlenecks and increase throughput. Which ones that are possible and cost-effective for your company depends on your unique situation. For example, if your existing system or design is not optimized, sometimes a relatively simple improvement can make a dramatic increase in throughput. At the other extreme, if you are highly optimized, you might have to implement several small improvements sprinkled throughout your system to get a decent throughput improvement. One possibility is to redesign your process to improve efficiency. For example, moving a station closer to a source of resources like parts, tools, or workers, automating an inefficient manual operation, or moving some work from one station to another. Decreasing the processing time of the bottleneck can sometimes be done if it's possible to do and/or doesn't affect downtime too much. Purchasing a faster machine is also a possibility. Similarly, decreasing the bottleneck's downtime or repair time can sometimes be done, perhaps through scheduled off-shift maintenance or purchasing a more reliable machine. If a setup is required at the bottleneck, you can look into decreasing that time, perhaps by adding another worker, streamlining the setup process, or purchasing equipment that requires less frequent or easier setups. If the bottleneck has high rework and/or scrap rate, you can look into decreasing those by purchasing more reliable equipment, switching from a manual to an automatic operation, or perhaps changing your process. If the bottleneck cannot be improved enough and space permits, adding a second parallel station may do the trick. If the bottleneck stations require workers, you may be able to speed things up by adding another worker to a shift or adding a part-time shift with fewer workers. Similarly, you might be able to increase throughput by increasing buffer size. If your process includes the production of different models or types of products, then changing how they are scheduled may increase throughput. Technomatic's plant simulation is the perfect tool to help you to not just optimize your system through what-if games with the above possibilities, but to identify the main bottleneck in the first place. As you may know, optimizing a non-bottleneck is a frequent and often costly mistake. So bottleneck identification is also very important. At worst, PlantSim can verify that your system is already highly optimized and that further improvements may not be worth the cost. And it's also a wonderful way to teach or show others how your facility operates. Our next topic will show how to optimize workstation throughput. In discrete event simulation, many workstations like drills, lathes, and CNC machines can be simulated with a single plant simulation station object, which can be viewed in 2D and or 3D. Here, an icon in the middle of the station indicates a part. LED lights indicate the state that the station is in. Red equals failed or down, as shown here. Yellow equals blocked, green equals working, etc. Note, the default 3D for a station can be changed to any 3D CAD file, so the plant simulation 3D view can look exactly like the real world if you want. Input data for stations always includes a processing time, in this case a constant time of 10 minutes. Sometimes it also includes a setup time, which you can represent a time to load a part, to change a welding tip after a given number of welds, etc. Here there will be a constant 2-minute setup for each part. Plant simulation gives you a choice of inputting failures or downtimes as availability and a mean time to repair, or a mean time between failures and mean time to repair. Here the station will randomly fail 20% of the time for a random time that averages 10 minutes. To simulate the operation of the station, we need a source to bring parts into the model and a drain to remove parts from the simulation and collect statistics. Now we can run the model. The statistics here for a 30-day, 24-hour-a-day simulation run. The throughput is 3.99 jobs per hour. Let's assume that we need to increase throughput. To do that, we can play what-if games, also called experiments. Unlike analyzing a line or a plant, we don't have to look for bottlenecks. Instead, we just change the input data that is changeable in the real world. We could do all the experiments manually. For example, if we run with no downtime, throughput increases to 5 jobs per hour. Of course, no machine is perfect, so that is unrealistic. Let's assume that the processing time cannot be changed with this station, but the availability might be able to be increased by doing preventive maintenance off shift, and that the setup time might be able to be decreased by changing steps that an operator takes to load the part or by having 2 operators do the job. Instead of doing several experiments manually, PlantSim's Experiment Manager lets you automate the process. Here we specify 11 experiments which vary failures by varying the availability from the original 80% to 100%. The results of the experiments are on the right. Of course, no machine is perfect, so 100% availability is totally unrealistic, but it does tell us that it's impossible to reach 5 jobs per hour without changing the setup time. Let's assume that it is possible to get 94% availability through either buying a more expensive machine or scheduling an off-shift preventive maintenance. But let's assume that we must get 5 jobs per hour. Maybe a faster machine is available, or we could buy a second machine of the same type, but that is overkill. So we could experiment by varying both the availability and the setup time. Since we are tweaking 2 variables, we can use the multi-level experiment option of the Experiment Manager, which allows us to set upper and lower levels along with an increment. This greatly eases the work you have to do for inputs. After you enter the values, the Experiment Manager automatically generates all the experiment combinations, which can skyrocket into the hundreds or more if you are tweaking several variables or finer increments. As you can see, in experiment 25, we can reach our 5 job per hour goal if availability is at least 90% with a setup time of 1 minute. The big question is, can the setup time be reduced to 1 minute? Perhaps a second worker might have to be added to get the job done, or maybe the worker's procedures could be changed. An ergonomic program like Jack or Process Simulate Human could be used to see if it is possible to do that. reduce the time to perform the setup, and to see if the worker can do it without too much stress and strain. If so, then the time could be entered into the plant simulation model's input data. So what can you do if the station performs more complex things involving several steps, like a robot making several welds? Perhaps there's an opportunity to improve the total processing time that is used in the plant simulation model. To study alternative welding paths, a kinematics tool like Process Simulate Robotics can be used. If an improvement can be made, then the reduced overall cycle time can be entered into the plant simulation model. So, like Process Simulate Human, Process Simulate Robotics can be used in tandem with plant simulation. Our next topic will show you how to optimize line throughput. This is a model of a line with 10 stations. A simulation run of 30 days results in a throughput of 2.96 jobs per hour. Our goal is 4 jobs per hour. We could open all the stations and look for bottleneck clues like lowest block time, highest working time, upstream stations blocked, and downstream stations waiting. We could run the simulation, then open each station and look at their statistics for these clues, but that's a tedious process with several stations. Instead, we can look at a time and state chart. Here we can see that stations upstream of station 7 are blocked, indicated by yellow color, and stations downstream of station 7 are waiting, indicated by gray color. So it looks like station 7 is the main bottleneck. It's obvious that the station fails a lot more than the others, indicated by red color. The bottleneck could be broke by decreasing the processing time and or setup time, or by decreasing failures by increasing the availability. Using the experiment manager, we vary station 7 availability from the current 60% to 100% in increments of 5. An availability of 85% results in our goal of 4 jobs per hour. If it is possible to increase that machine's availability, then we're done. Other possibilities are decreasing the processing time and or setup time, or replacing the machine with a more reliable or faster machine. Plant simulation also has a unique tool called the Bottleneck Analyzer, which has 2 options. The first option is Show Analysis, which places miniature time and state charts above each station. Here, like the single time and state chart, you can see that the stations upstream of station 7 are blocked, that the stations downstream of station 7 are waiting, and that station 7 has a much larger failure percentage. Another great option of the Bottleneck Analyzer is the ranking option. This can be a tremendous time saver for finding bottlenecks, especially if there are a lot of stations. Here, the top object, station 7, appears at the top of the ranking list. Note that disruptive indicates failures. Often the top object is the main bottleneck, but not always. For example, if the stations that a part flows through vary according to part type. But objects at the top of the list are prime candidates for further analysis and experimentation. This dramatically decreases the time it takes to locate bottlenecks. Our next topic will show you how to optimize plant throughput. This is a model of a plant that grinds, drills, and polishes gizmo and gadget parts, then assembles them into a whatchamacallit product. Running the model for 30 days results in 4.05 jobs per hour. The goal is 5 jobs per hour. Optimizing plant throughput is similar to line throughput, so we could save time by locating bottlenecks through a single time and state chart, but let's use the ranking option of the Bottleneck Analyzer. You can see that drill gizmo is blocked 26.92% of the time. And you can see that the bottleneck is polish gizmo. Since processing time cannot be decreased, setup time must be decreased. One possible solution is to use another polish gizmo station, or we could get a machine that automatically loads the part. And this would eliminate the need for a worker to load the part too. To simulate an automatic loading drill gizmo, all we have to do is set the setup time of polished gizmo to 0 and eliminate the need for a worker. This boosts throughput from 4.05 jobs per hour to 5.16, a bit more than our 5 job per hour goal. So we're all set, or so it seems. Just when you think that all is well, your CEO yells out, "What the hell is wrong in our Hell, Michigan, whatchamacallit assembly plant? I thought you promised 5 jobs per hour. Instead, it's getting only 4.18 jobs per hour. If you don't find a solution ASAP, you'll be fired." At first, you're puzzled. Your whatchamacallit assembly plant model has the latest input data, and the model runs at a bit more than 5 jobs per hour. Then you realize that the model assumes gizmo and gadget parts are always available from the sources in the model. So you use PlantSim's hierarchical modeling capabilities to quickly create an integrated enterprise model that includes all the latest data from all 3 plants. The top level view looks like this, but inside each plant icon are full simulation models lower down the hierarchy. Sure enough, using the 2 plant models to feed the assembly model results in only 4.18 jobs per hour. Finding the bottleneck without the bottleneck analyzer would be cumbersome. As you can see, row 2 shows that the drill gadget station in the whatchamacallit assembly plant is waiting 24% of the time. The bottleneck happens to be at the top. The grind gadget station in the gadgets part plant, which has failed or disrupted 29.8% of the time. That station is old and in need of some new parts. After the repairs are done, all is well again in Hell, Michigan again, producing the goal of 5 jobs per hour. You have seen how the experiment manager can automate the running of several simulation runs by varying 1 or more parameters. But what if things are more complex and you need to vary numerous parameters with numerous values that result in thousands or even millions of possible combinations? An example is a plant that produces numerous parts, each one having different processing times. Optimizing the scheduling of parts like that can be dramatically increase throughput. The experiment manager can do that, but you'd have to wait a long time for the numerous runs for every variation to finish. Genetic algorithms can help you to quickly find a near optimal solution by trimming down the total number of simulation runs. The algorithm's procedures find a very good approximation solution based on random search in a reasonable time. The professional version of plant simulation has a GA wizard which facilitates the setup and runs that provide a quick near-optimal solution. The layout optimizer uses genetic algorithms to minimize transportation costs. Energy optimization is becoming increasingly important. It's a win-win situation since it saves money and helps the environment. Energy pain points include rising energy consumption and costs. Also, green is in with consumers and regulators. Additional green certifications like the Energy Star seal and EPA regulations and mandates are becoming more important. The solution to these problems has 2 ingredients. First, dynamic simulation modeling of systems using a tool such as Siemens Technomatics plant simulation software provides a powerful virtual environment to test and improve a system's design and operations to address traditional optimization issues such as maximizing throughput, minimizing inventory and buffers, and minimizing labor. Second, while plant simulation always provided a powerful engine to build, analyze, and optimize your processes, the relatively new energy features that were added to PlantSim now let you simulate energy consumption and analyze and optimize energy efficiency. Note, the new energy features are incorporated into the base plant simulation product, as can be seen in the new Energy tab that's added to the other input-output tabs for standard plant sim objects that model stations, machines, conveyors, etc. And now we have a video of an energy optimization of an LCD TV flat screen production facility. Start with a screen tour of our plant simulation model. The source puts skids on the conveyor to the right, which moves skids up to the main assembly line. The main board is placed on the skid at station A1. The display panel is added at station AS3. Other parts are added further down the assembly line. And then the panel goes through quality, localize, inspection, packaging, and labeling processes before being removed from the skid and transferred to the finished product drain where throughput statistics are collected and displayed. Using plant simulation's powerful traditional modeling and analysis tools, the existing model was optimized for a maximum throughput of 1,976 screens per day. What-if experiments also showed that a minimum of 80 skids was required to maintain that throughput. Since plant simulation now can model, analyze, and optimize energy consumption, we set new goals for our plant to reduce energy consumption without decreasing throughput. The first step is to specify power inputs in kilowatts in the Energy tab of the stations for all its states, including working, setting up, operational, failed, standby, and off. We also specify the transition times between states. Now we'll run the model for one simulated day. We'll run the model slow for a while so you can see everything in action, starting with the first skid being placed on the main line and throughput statistics being collected when the screens are removed from the skids after the packaging line. After 1 day of simulated time, you can see that our throughput is the optimized value of 1,976 screens that was mentioned before. Since we added energy inputs for our stations and conveyors, the Energy Analyzer's display panel also provides valuable overall statistics, including 1,899.7 total kilowatt hours of energy consumed. Let's take a look at the Energy Analyzer's Show Visualization option. The stations surrounded by solid red circles are the ones that consume the most energy. Hollow red circles indicate the next largest energy consumers. Blue indicates the least energy consumers, and purple is in between. This visualization lets you quickly identify areas where you may want to focus on making potential individual energy improvements. This is similar to using PlantSim's Bottleneck Analyzer to help you to identify the main throughput bottlenecks. Instead of diving into individual station details, let's take a look at the Energy Analyzer's Show Plotter option. This shows kilowatt consumption at any given time. As you can see, from midnight until the start of the one shift we are working at 8 o'clock in the morning, all the stations and conveyors were in operational or waiting state and consumed approximately 77 kilowatts. Then at 8 o'clock, the equipment switched to working state and consumed about 85 kilowatts. During the 15-minute break at 9 o'clock, equipment switched back to operational. Then back to working state until lunchtime. During the 45-minute lunch break, the equipment switched back to operational. After lunch, we're back to working state. At 2 o'clock p.m., we're on a 15-minute break, so we're back to operational. Then back to work after the last break of the day. Then back to operational state from the end of the shift at 5:15 p.m. until the end of the day, since we are only working one shift. After looking at this chart, you may have guessed that we could save energy by switching to standby during breaks instead of leaving everything in the operational state. To do that in our model, all you have to do is check the on-screen Save Energy Standby During Breaks checkbox. Now, after running our model for 1 day, our Energy Analyzer's display panel shows that we've decreased total power consumption from 1,899.7 kilowatt hours to 1,820.9 kilowatt hours. This would result in a nice decrease in your energy bill over the years. Also, we achieved these savings without any decrease in throughput. Let's take another look at the Energy Analyzer Show Plotter option. Instead of being in the operational state consuming about 77 kilowatts during breaks, our equipment is now in standby state instead, consuming only about 14 kilowatts. After looking at this chart, you may have guessed that we could save even more energy by switching to the off state during off shift or unplanned time, instead of leaving everything in the operational state. Since these periods are long, we are switching to off state instead of standby for even more energy savings. To do that in our model, all you have to do is check the on-screen Save Energy Off During Night checkbox. Now, after running our model for one day, our Energy Analyzer's display panel shows that we've decreased total power consumption from 1,820.9 kilowatt hours to 819.1 kilowatt hours. And once again, we achieved these savings without any decrease in throughput. Let's take another look at the Energy Analyzer's Show Plotter option. As you can see, during off-shift or unplanned time, instead of consuming approximately 77 kilowatts, our equipment is consuming just about 8 kilowatts. And during breaks, instead of consuming approximately 77 kilowatts, our equipment is consuming about 14 kilowatts. The secret behind modeling these energy-saving measures is the State Transitions button on the Energy tab for our station and conveyor objects. The left side tells PlantSim what to do at the start and end of a pause or break within a shift. Here, standby is specified. The right side tells PlantSim what to do at the start and end of unplanned or off-shift time between shifts. Here, off state is specified. And last but not least, the Power Up Early option lets you power up equipment early so that your equipment is ready and raring to go as soon as working time pops up, so you get no decrease in throughput. Now, if we look at the Energy Analyzer's Show Visualization option, we can see things have improved, but power supply stations 1 and 2 are still high energy consumers, as indicated by the solid red circles. If we look at the Energy Analyzer's Show Chart option, you can see that the power supply area consumes a lot of energy while in the operational state. We can see the details by highlighting the area in the chart. The light green areas for power supply stations 1 and 2 show that these stations consume a lot more energy in the operation or wait state than the other stations. While running the simulation, it appears that the power supply buffer is always full. A look at the buffer's chart shows that it's almost always full with 150 power supplies. Every time a power supply leaves the buffer for the main line, the power supply line puts in one more unit, hence the near straight but jagged line. One potential energy optimization opportunity in this area would be to treat this buffer as a Kanban buffer, where the power supply line feeds the buffer only after it reaches a lower level of contents. In our model, the Save Energy Power Supply checkbox sets the power supply line up so that the buffer is filled at the start of the simulation, and thereafter it's fed only after 50 units are left in the buffer. Now, after running our model for one day, our Energy Analyzer's display panel shows that we've decreased total power consumption from 819.1 kilowatt hours to 755.9 kilowatt hours. And once again, we achieve these savings without any decrease in throughput. Finally, if we take another look at the Energy Analyzer's Show Visualization option, we can see things have improved dramatically in the power supply area. Instead of solid red circles indicating high energy consumption, power supply stations 1 and 2 are now purple, indicating a medium level. There is room for even more optimizations, but I hope you've seen enough to see how useful Plant Simulation's new energy optimization features can be. I hope you appreciate the value of those new features with the energy features in Plant Sim now. Version 15, a major full upgrade of Plant Simulation, was released earlier this year. Like all new versions, there are several useful new objects, and I thought I'd show you a few of them. A great new cost feature has been added that lets you optimize your facility cost-wise. In the past, you would have to create your own attributes and programming to do what is now built in. A new cost tab appears in the material flow objects. Non-length objects like the station, assembly station, and robot have 3 fields: depreciation period, investment costs, and operating costs. Length-oriented objects like the conveyor, track, and angular converter have 2 more cost per length fields. And parts and containers have a material cost per piece field. The new cost analyzer gathers the costs. The corresponding HTML report shows total costs for the whole model, total costs and subframes of the hierarchy, and individual costs for objects, parts, and containers. The new AGV pool and marker object to the right of it, which looks like a bullseye, simplifies the modeling of AGVs. Similar to the worker pool, the AGV pool brings transporters into the model. Instead of requiring tracks to move on the AGV moves according to a programmed sequence of markers, so virtual tracks can be programmed on the fly. The lift object lets you model an elevator with great 3D visualization. It was added in the recent version 14.2 patch. The Gantry loader lets you model an overhead gantry. It was added in the recent version 14.2 patch also. There are numerous other additions and changes in version 15, too numerous to mention here.